Okay, welcome. So if you recall, in the last class we had ended the lecture with telling you how to derive the different expressions of the current. The most important thing is the profile of minority electrons in the base. Okay, I am talking about NPN. So the base is p type dope. When you are injecting electrons from the emitter to the base by forward bias, okay, the electrons will recombine and decay in the base. The base is very short. Why? Because then only that will make sure that very few electrons are recombining in the base, so that majority of the electrons reach the collector and come out. Otherwise, most of the electrons will recombine in the base, very few electrons will come out from the collector, you will not get good current out of the device. Okay. So the base, in the base when the electrons are injected, they will decay almost linearly, and we discussed that that profile of the minority carrier electron in the base is the most crucial actually. Okay. So we will take a recap from there and we will quickly finish up the expression for the base, emitter and the collector current, so that we can actually understand the transport ratio, the beta, the gain, the base transport factor, all these things can be expressed in terms of proper quantitative definitions. Okay. So we will come to the whiteboard again here. So if you recall from the last class, I told you this is your base, this is your emitter, this is a collector, there is a small depletion here, sorry, and then there is a large depletion here. Only this matters, which is WBN. The electrons that are injected from the emitter side will decay almost linearly, okay, almost linearly it will decay, and that profile, the minority carrier profile, is NBX. If you take the slope of that profile here and multiply with QADN by Ln, that is the diffusion coefficient things and all, you will get, and the slope here, you will get the current that is coming from the emitter side because of electron. And if you take the slope here and you multiply with this quantity, you will get the current that is going out there because of electron. Of course, there is a base collector reverse leakage current which I am neglecting here, but there is a small base collector reverse leakage current here, and the difference of this and this should ideally give you the recombination current that is taking place in the base because of the electrons that are going there. No, they will recombine in the base, that current will come out from the difference of this and this. Of course, there is a back injected current here, holes, that is very easy to explain, right. So let us write down the equations for the current here. Okay. Let us write down the equations for the current here. If you recall, the first expression is actually, so let me go to a new page actually. So IE, the total emitter current, okay, the total emitter current will have to consist of two quantities. One is the IEN, that is your electrons that are injected from here, okay, which I told the slope here multiplied by this. Okay. Of course, I did not write down the expression for this profile here. This base profile NBX actually is its expression depends on sine, hyperbolic and other things. It will all be uploaded in the notes, so not a big deal, but it's close to being linear but not exactly linear. Okay, we know the two boundary condition, by the way. We know the two boundary condition, the total carrier here and the total carrier here, that is the boundary condition, we know that. So so essentially what's going on here is that you have the emitter current which has two components, sorry. One is the electron injected component IEN and one is the whole back injected component IEP. So this component is actually can be written as Q A, I told you, right, dN by Ln. This is basically in the base, right. Ni square by the base doping, this is the minority carrier electron concentration there, into cot hyperbolic, there is a hyperbolic function here, of the base width. This is the neutral base width, WBN is the neutral base width, remember this is the base width, actually not the true base width but this base width, edge of depletion to edge of depletion, that is what matters actually. Okay, edge of depletion to edge of depletion by Ln, this is the diffusion length. Okay, this of course this times e to the power QVBE by KT minus 1, that is your the forward bias voltage that you are applying. Of course, it depends on the voltage. If you don't apply voltage, you will not get any current, plus this component which is basically easy, it's an exponential decay QADE by LE, because this is the holes that are decaying in the emitter, into Ni square by N emitter side doping. Okay, that's you can increase the doping and make this quantity become very small, that's the idea, into e to the power QVBE by KT minus 1. So I can write the emitter current as this quantity, okay, that quantity plus this quantity, that quantity, whole thing into exponential of EQVB by KT minus 1. Okay, that will what will come to be. Similarly, if I take the slope of the minority carrier concentration here and I multiply by this, I get the collector current, right? The collector current because of the electrons that are coming out, right? So the collector current because of the emitter, the electrons that are reaching there, and I am excluding the base collector reverse leakage current, that is because it's very small. So then this component will come out to be the slope of that, no? So that will be q a dn by ln into minority carrier profile, which is Na by Nb. This is all PN junction thing basically, okay, into 1 by sine hyperbolic, because the minority carrier profile has hyperbolic functions, sine hyperbolic into Wbn by Ln, okay, and the whole thing of course has to be multiplied by e to the power qvb by kt minus 1, okay. That's your collector current. And the base current will therefore be the difference of the emitter current, the total emitter current minus this current, the collector current because of the electrons. I am neglecting the base collector reverse leakage, by the way, okay. So if you do this, you will get two components of the base current. Of course, one is the back injected hole, which is this. This is an emitter current, but also this is there in the base component, you can think of it. So that component will come, that component is q a de by le ni square by nde, right, into e to the power qvbe by kt minus 1, right. Plus there is another component, this component comes because of the recombination, that is q a dn by 2 ln square, because if you subtract this sine hyperbolic and this cot hyperbolic, the functions will come, the difference of cot hyperbolic and sine hyperbolic function, that can be approximated by some Taylor series, and that's why the hyperbolic function is gone away. So 2 qa dn by 2 ln square into the minority doping ni square by nab into wbn, which is your minority carrier, the base neutral base width, into e to the power qv, the same thing is there actually, qvbe by kt minus 1. So please recall that this quantity is because purely due to the recombination of electrons in the base. This is because of recombination of electron injected from emitter, okay. This is electron because of recombination of electron injected from emitter with the holes in the base, So electrons that are injected from the emitter will be recombining with the holes in the base. So that recombination gives rise to this particular component of the current. This is the back injected component, and this can be made very, very small, by basically changing the doping here. This also we want to be very small basically, okay. So for this to be small, your base width has to be small, because the base current should be very tiny, and if the base current this width is small, then also you can actually have a higher gain, will come to that, okay. You also want this quantity, you cannot make it arbitrarily small now, that is large or small, because if this quantity is very small, then this might limit your base current. So then you don't want this base doping to be super light, because then your base current will increase, which is not what you want, okay. So these are the components, and depending on the question and the numerical that is asked, either both or one of the components will become predominant in the question, okay. This is a base current, we know the base current, we know the collector current, this is the collector current essentially, remember, and this is the emitter current, this is the whole thing is emitter current, this plus this. So what we can do now is that I can define that you can define the base transport factor. Base transport factor, if you remember last class probably we had discussed, base transport factor B essentially tells you what fraction of the collector current, because of the electron collector current, not the base collector leakage current, what fraction of the collector current actually comes from the electron emitter current, not the total emitter current, the electron emitter current. So if you take the expression for the collector current and the emitter current from the 2 slides before, then this ratio will come out to be actually 1 by cos hyperbolic WBN by Ln, okay. So 1 by cos hyperbolic WBN by Ln, this whole thing can be approximated as 1 minus WBN square by 2 ln square. Okay, so this is your beta, the B, the base transport factor. So the base transport factor becomes better, or it improves, if this quantity becomes slower, which means this quantity has to approach 1, which means the base width has to be narrow. So a narrow base width also helps, a narrow base width also helps improve your base transport factor. Okay. Similarly, your gamma, the injection emitter injection is efficiency is defined as the total fraction of emitter current, which is your electron current. So this is total fraction of emitter current is IEN plus IEP. So if you put down the expression for IEN and IEP, there's no base component here, by the way. Okay, all these things, then you will find out that the emitter injection efficiency, okay, the emitter injection efficiency gamma can be written as 1 minus base doping. These expressions I am taking from the previous 2 slides. Okay, base doping, excuse me, emitter doping, diffusion coefficient in the emitter, diffusion coefficient in the base, base width, neutral base width WBN divided by the emitter effusion and the diffusion length in the emitter. You want this quantity to be as small as possible, so that the entire this quantity becomes as close to 1 as possible. So the emitter injection efficiency you want to be 1, which means you want that most of the electrons, actually the most of the emitter current is because of electron current and not because of the base injected hole current. Remember the thing. So for that you want the gamma to be close to 1, and you can get gamma close to 1 when your base doping is much lighter than your emitter doping. That also helps your other things, and when your base width also is narrow. So eventually this all boils down to the fact that base width should be narrow and the base doping should be much lighter than the emitter doping, in which case you can improve the gamma, you can also improve the base transport factor. Okay, and of course the collector the current transfer ratio alpha is actually given by B times gamma. So the product of the product of essentially this quantity and this quantity will give you alpha, and so if this improves then alpha will also improve. And finally we have beta, which is your basically the total current in the output by the base current. Now base current has 2 components. One is the back injected current component, which is like QADE by LE Ni square by NAB into e to the power QVBE by KT minus 1. And another component is the base recombination current, true recombination current, which is QADN by 2 ln square Ni square by NAB. This is the base doping the minority base into WBN into e to the power QVBE by KT minus 1. Okay, KT minus 1. Okay, you can understand that, right? This is e to the power QVBE by KT minus 1. Okay, so these are 2 components. Now if I assume that this component dominates, this is the primary component, then your beta will be given by this ratio, if you can plug in this expression from the 2 slides before. Okay, if you take the 2 slides before, then the ratio will come out to be around the emitter the base diffusion coefficient by the emitter diffusion coefficient. Okay, emitter coefficient diffusion into the emitter diffusion length by the base neutral base width into emitter doping by base doping, sorry, this is NAB. So your beta, this is your gain, by the way, direct gain. Your gain can be increased if your emitter doping is much higher than the base doping. That's what we have been telling you. And if this quantity is very small in the denominator, which is the base width should be narrow, because these other 3 quantities are constant, you don't change them so much. You increase the emitter doping, which is the same thing, right, as we have talked about in the emitter injection efficiency and all. Reduce the base doping and reduce the neutral base width, right, neutral base width. Make the base shorter. So if you satisfy these 3 conditions, your beta will go up. And of course if your beta is dominated by this, then your gain beta will look like 2 into ln square by WBN square. in which case also more than doping your base width should be narrow. In that case the base current will become smaller and your ratio, your gain actually will become larger. Okay. So, these are the ways in which you can actually make the transistor have a higher gain and make it a better device. Okay. But there are some price you have to pay, you do not get all of these things free of cost. So, one problem is that what is one problem? One problem is that your ideally, okay, I understand that there is a depletion here, there is a small depletion here because of forward bias, there is a large depletion here. This collector pe whatever collector voltage you are applying, like this is your whatever output characteristics and this is your collector current. The collector current here does not depend so much on the collector voltage. Okay. The collector voltage after it becomes this flat saturate, the collector voltage does not actually have an effect on the collector bias. But if you are for increasing the gain, or for making emitter injection better, alpha better, B better, if you want to make all this better, okay, then your base width should be narrow, WN should be narrow, that is one thing, and the base doping p type doping in the base should be low. You remember that emitter base doping should be much higher than the base doping, emitter the n type doping should be much higher than the base doping. If that is the case, then base doping will be light. If the base doping is light, okay, so if the base doping is light, okay, if the base doping is light, then what will happen is low. If the base doping is low, you will get very high gain, nice, very high gain, very high transfer ratio, very good things will come, but there is a price that we have to pay. If the base doping is low, then every time you increase this collector voltage from say 3 volt to say 6 volt here, if you increase the collector voltage, reverse bias voltage from 3 volt to 6 volt, then this depletion will increase, and this depletion will come more and more towards the lightly doped side, if you recall. So, the base side is lightly doped, so the depletion will keep coming more and more, which means this width, the neutral base width WN, will depend as a function of the output voltage. It is a function of the output voltage, which means your current here will not be independent of this voltage, but it will increase as you increase the voltage. So, it will be something like that. Instead of saturating, it will go like that. So, the family of curves will look like that. It will not saturate, which means the output current will also be a function of the output voltage. Why? Because if your output voltage increases in reverse bias, then the depletion increases, the depletion extends towards the lightly doped side. If the base is lightly doped to get high gain, then your depletion will extend towards the base. So, the base width becomes narrow. If the base width becomes narrow, the current becomes high. So, then it behaves like a resistor. It basically loses the transistor action. It is like a two terminal device, a resistor, where you are increasing the voltage also increases the current. It is nothing unusual about it, it is like metal. You increase the voltage, you increase the current. That is not how a transistor should behave. So, you lose the transistor action, and this width of the base becoming less and less with this is called base width modulation. This problem is called base width modulation. This base width modulation also is called early effect. This name is not called early effect because it is happening early or something. The person who discovered this, his name was early actually. Okay. So, this is an early effect kind of phenomena, where you basically have a change of base width with the higher doping, and that is why your output current never saturates. It is like a resistor, you defeat the transistor action. Okay. And if you look into that output characteristics, say IC and this is VCE for example, it will look something like that. Okay. If you actually backtrack all this, they will all meet at one point. They will all meet at one point, and that is called some minus VA, right, somewhere it will meet. It is called early voltage. Ideally, you want the early voltage to be minus infinite, because if this is exactly parallel, a transistor should have this saturated current exactly parallel. In this case, this will never meet. So, this is infinity. So, in other words, you want the early voltage to be as large as possible in terms of negative, absolute negative value. Okay. you want it to be as large as possible. So that will be only possible when your base is heavily doped. When your base is heavily doped, then the depletion you have here will not extend into the base so much, but will extend to the collector. Only if you heavily dope the base, your base width will stay normal. That is, the width towards the base will not be so much. But if you dope the base high, then your gain will be low, your emitter injection efficiency will be low. So basically you have to make a trade off between the early voltage, you have to make a trade off between early voltage and gain or gamma or beta or alpha, whatever. So everything does not come without any effort. There is a price that you have to pay. Either you get high gain, or you basically have to sacrifice the output conductance here, and you will get a not so good device. Okay, you will get a not so good device. So that is called early voltage, and this early voltage, the VA that I told you, okay, this VA has actually a term, and that VA can be mathematically expressed as the total majority charge stored in the base, total majority charge stored in the base. So what is the total majority charge stored in the base? Divided by the base collector capacitance. Okay, base collector capacitance. Now the total charge stored in base, the majority charge stored in base, can be called Qg, and that is basically your doping, the majority doping that you have over the entire base width, 0 WBN. Okay, and this is called, this is almost equal to NAB into WBN for uniformly doped base. This is called Gammel number. Gammel number. Gammel number basically tells you the total amount of positive, majority positive charge here in case of NPN. In case of PNP, it will be majority negative charge. The majority positive charge stored here in the base, in the neutral base width region. Okay, neutral base width region. This is called Gammel number. And the base collector capacitance is given by epsilon naught epsilon A, area of course, divided by the width of the base collector depletion region. Remember, the base collector depletion region width, this width, whatever this width is, WBC. In the base collector junction, there will be depletion width there. That is the ratio. This gives you the early voltage is therefore given by the base doping into the base neutral base width divided by epsilon naught epsilon S into A divided by WBC, or can take the WBC upwards. So WBC. Okay, this is roughly your base emitter. Sorry, the early voltage. You want the early voltage to be as large as possible. Only then your output saturation will be good. So for having this large, your base doping also should be high, which is in contradiction to the gain thing. So I told you already that the base doping should be high. Base width should be high, but let's not touch the base width so much, of course. And the base collector width should be also large. Okay, or in other words, the capacitance should be small. The base collector capacitance CBC should be small, but which means the base collector depletion width should be large, and because base doping is high, it means the collector doping should be very light. Collector doping should be very light, very low. Only then the base collector depletion width will be large, and in that case you will define an early voltage which is very large. Okay. So that is an interesting thing that we learned. So what are the things we learned? We have learned the base transport factor, the gain, the emitter injection efficiency, the current transfer ratio. We have expressed that in terms of the current. We have given some mathematical expression. We have given some mathematical expression to that. Then I told you about the early effect. And how this early effect trades off with the base, with the different parameters for gain and current transfer ratio and so on. This needs that the base doping is high. Okay, and this needs that the base doping should be low. So this is a problem that we have. In other words, also if you recall, this also wanted that your emitter doping should be high. Emitter doping should be high. Okay, emitter doping should be high. But there is a problem with emitter doping being high. So you see, this is a base collector junction, this is a this, this is a this, and this is a this. So you see the base, this emitter cannot be arbitrarily, okay, highly doped. You cannot arbitrarily dope it like say 10 to the power 19 or 5 into 10 to the power 19 per centimeter cube. You cannot dope it arbitrarily high. Why? Because there is a problem that will come very soon. You want to make high gain, high transfer ratio, you want to dope it very high, but you cannot, you should not. If you dope it very high like 5 into 10 to the power 19, your beta, your gamma, everything will become very small. Okay, there is a problem because of some twitch, your everything will be sacrificed if your doping is arbitrarily high here. What is the problem? Can you think about it? What is the problem that will arise if your emitter is arbitrarily highly doped like 5e19 or 10 to the power 20 per centimeter cube? If you dope it ridiculously high, what is that most important problem that will lead to the device having almost no gain? Can you think about it? You should think about it over this now gap that we have. So we'll end up the class here now. In the next class, we will discuss what is that will actually affect the device performance when you dope the emitter extremely high. I will leave you with that question. Think about it. What is the main problem that comes when you dope a material very high? And the moment you know about it, you will understand that if you dope the emitter very high, all the benefits that you are going to get out of the transistor in BJT will actually be defeated. The purpose will be defeated. You will not get those. Okay. All the discussions that we have had, early effect, gain, transport factor, everything will go for a toss. Everything will go for basically low. Everything will be bad if you dope the emitter extremely high. Okay. What is it? So that we will start in the next class, and we will also finish up more other important things of the base of the BJT, like some of the nonlinear effects perhaps, and also we can solve some of the numerical problems of BJT. And we will also try to see if we can cover delay in the next class, like what is the speed at which a transistor can operate, what is the fastest speed a transistor can operate. Okay. So we will end the class here today. Please think about why emitter cannot be doped extremely high. Okay. In the next class, the first thing we will begin is to understand why the emitter cannot be doped extremely high. Okay. Thank you for your time.